Welcome to the fourth part of the database querying with R tutorial. So we have covered what our database is and how to get set up and how to use a database locally, and now we're going to actually access the on-farm database that is hosted in the Azure cloud currently. So again, you can get to this document from the GitHub repository. This is, number 4 here, and you can also download the R notebook right here, and that is what we will go to now. So the first thing that you're going to need is credentials to sign into this database, since it's password protected. I have a file here in the repository called secret example. This is what it's contained. You need to contact one of the data managers on the team to get all of these filled in with a username and password for yourself. And then you can fill this in, resave it as secret.r right here, and then run it. And again, I have a cleanup chunk just in case there's anything floating around. And then let's go ahead and make a connection. And you'll notice that this took a second right here before it returned me back to the console. Depending on network traffic or how good your Wi-Fi is, sometimes it can take a minute to return the connection. And if you try and interact with R before that is completed, sometimes it'll cause some errors, so just be aware of that. Again, remember to close your connection when you're done with it with db disconnect. And if your Wi-Fi is spotty, like I mentioned, you may need to reconnect occasionally. If you've been inactive for a while, you may need to reconnect, so just be aware of that. There are some arguments that we put in here that are not the defaults. So in particular, this big int equals numeric. I'm fairly sure that the only data type that is in our production database that is what's a so-called big integer is the row ID column. But just in case, we're telling Postgres that if you have any 64-bit integers, return them as native base R numerics, which are 32-bit numbers. I kind of go into some of the details, but you probably don't really need to worry about that. Just know that you probably don't want the default of integer 64. So let's see what's in the database. Again, we're going to run db list tables, and you see that there are a whole bunch of tables, many more than in our toy database that we used in the last tutorial. These are fairly self-explanatory from their names, what might be in the table. There are these two here on the ends, PG stat statements and PG buffer cache. You likely won't have read permissions for those. They have to do with some internal workings of the database, so just don't worry about those. So let's look at a table. Here we're going to look at the CC species table. You see that it gives us a list of species and what family that they're in. And this is the whole table. So in the last tutorial, we talked a lot about the difference between completed queries and lazy queries. This was 23 rows, so not a huge deal to just return the whole table instead of a preview. But some of the tables have a lot more rows than that. So let's actually figure out how many rows are in all of the tables of the database. So this code chunk that I'm about to run is a whole bunch of functions that aren't in those sort of required packages. You don't really need to know what all of this does, although I do kind of explain it in the web page version of this document. But let's just see. And this is going to take a little bit to run, about 11 seconds, because it is kind of a heavy computation to be doing on the database. And you can see while it's running, I had that little red square there instead of the play button. So here you can see it's returned the number of rows that are in each of the tables of the database. So you have some tables that only have 3 or 3,000. But then you have the weather table, which is over 1 million rows, almost 1.5 million rows. If you request the whole thing of that, it will take a few minutes to return everything. It might crash your session, et cetera, et cetera. There are situations where you might want to bring it all in, and then there's ways you can allocate memory for it. But in general, you probably want to run some kind of lazy query, build it up incrementally, and do that instead of pulling the entire table all at once. And again, this is the explanation for the chained code that I just wrote there, which I would recommend that you follow along in the web page tutorial. So now we have looked at what's in the database. Let's make some simple queries. So let's look at the site information table. This is a super important table because it is the equivalent of the old Google Sheet that we had, where that's where you started filling everything in. This is how the code is keyed to everything else. And the command that we just ran here, tibble on the connection object with the site information table, is exactly the same as if we ran select star from site information in vanilla SQL. So let's see a few simple queries. Like I said, here we're going to take the site information table, we're going to sort it by year. We are going to divide all of the rows into groups by year, and then we're going to get a count of how many rows were in each year. So you can see that we had 36 sites in 2017, 43 sites in 2018, and 55 sites enrolled in 2019. And then I ran show query, because again, this is a lazy query, this all happened on the database, to see what is the actual information being sent to the database in raw SQL. And this is, you could write that by hand, certainly, but it's starting to get to where, I would need to look up exactly what the syntax is. And so I am generally not going to be using much of the vanilla SQL from here on out. So again, this happened in the database. Let's pull this in locally and do some computation on it. So this is the exact same code that we just ran, except then we end it with this collect, which pulls everything in from the lazy query to a local database that's stored in memory in your R session. And so here we have this site list object, which we're going to come back to in just a second. But again, before you run any kind of query, you probably want to check and see how many rows that is going to return. Here it only returned 134 rows, so not a big deal. So an example of something that you can't do in the database, but you can do in your local R session, is visualization. So again, this is going to use some of those super optional packages that you don't really need. So if you don't care about the visualization and you just want to kind of follow along, you don't have to install those, but I am using them here. In particular, the R Natural Earth package, ggplot, SF, which is simple features, it's for spatial information. And so let's see what happens when we run this chunk of code. So you can see it kind of gave us 3 pages of output here. This one is just a warning message, but this first one is a map, that shows where the sites were. This is a static image that, you could customize it however you want and embed that as, in a paper that you're writing. And this is an HTML widget. So this is sort of a web page embedded inside your R session, and it displays the same in the web page version of this document as well. And so this is kind of more like an online map that you might be used to. And I did put some bounds on it just so you can't zoom in all the way. Since these documents are public, I don't want to share any sensitive data. So I talked a lot about, if you had a table that you had lots and lots of rows, that you might not want to return all of them. So let's look at a preview of the weather table. You can see that there are a number of columns, an unknown number of rows, although since we already did that computation, we know that it's quite a few. And in the last tutorial, I showed you how you can filter your queries on text fields. Remember, we were looking at where the crop was equal to the string corn, and also on numeric, where you can do greater than, less than, things like that. But here in this table, we see that there are two new data types that we hadn't seen before. We've got date and we've got date time. Dates and times are famously difficult to work with. There are several packages in R that try to work around how difficult they are. I'm going to show you one of my favorites. But in pretty much every programming language, it's well established that dates are just a real bear to work with. So here are two of the approaches. Here you can see that I've formatted a vector of dates with the sort of YMD format, and then I've got some times in what you might call, somewhat standardized. I've still got the AM, PM, and then I've got completely unambiguous times in the ISO 8601 format, where you've got YMD, HMS using 24-hour time. And so this is the sort of base R version, where you're using as date, you're using as POSIX CT, which goes back to the days of when things were stored in Unix time. And you can see that you have to pass in these extra formatting strings, and it can be kind of difficult to work with. This is the version that uses the package that I like called Lubridate, which makes working with dates smooth. And you can see that it does a lot better job of guessing what format you want these dates to actually turn into. And so you can see that we just took a text string. This is just a plain character right here. And by running as date time, we turned it into a date time formatted object. That's really important because the dates are stored in the Postgres database as dates and date time objects. And so if you just pass in a character, it won't know what to do with it. So for example, if we wanted to say, July 4th, we could test on where date is exactly equal to July 4th. And you can see that we got our return here, which is all of the rows where date is equal to July 4th of 2018. And this is the SQL query that was sent. Select star from weather where date equals cast 2018-07-04 as date. And we can verify that we got everything that was in the table by asking, for each farm, how many rows were returned. And we see 24, 24, 24, so one row for every hour of the day. But we can also do that with times instead. So let's say we want to say that time started at midnight on July 4th and ended 1 second before midnight on July 4th. And then we want to run a query where we're filtering the time column between these two times and see what gets returned. Again, it's pretty much the same observations, and we have 24 observations per site, so we know that we got all 24 hours. You can see that the SQL that's returned is slightly different because it is time instead of date. However, you should know that time zones are easy to trip up. They automatically assume that the code that you're writing is for your local time zone. And you're probably on the East Coast of the US, maybe in Central Time, maybe on the West Coast. But the times in the database are stored in UTC time. So it automatically generates an offset, which, because we asked for July 4th, is a -4 offset because of daylight saving time. If I were to ask for a date that is right now, it would be a -5 offset because it's winter. So just be aware that you might have to play around with time zones depending on what exactly you want to be filtering for. So joins are, like I mentioned in the last tutorial, this whole complex thing that's hard to wrap your brain around. And I do really recommend looking up some diagrams, looking up some other tutorials specifically about joins. I provided a link in the last tutorial to one that I found really helpful, so go check that out. But like I mentioned, the site information table has the keys with the code and then all the information about the farm sites. So the state and the year and the GPS coordinates. So if we want to do any kind of analysis, we have to combine the table that has the measurements that we want with the site information table. So let's look at the decomp biomass table. You can see that we've got our list of codes, we've got our subsamples and our subplots, we've got the time that the bag was picked up, bag 0 through 5, we've got the empty weight, the fresh biomass weight, a whole bunch of other variables related to the litter bag decomposition study. So if we want to try and analyze this relative to, for example, states or years, we need to join this back into the site information table. If you look at how many rows there are in the decomp table for each site, you'll see that there are about 24, assuming that no bags got, damaged or destroyed. And there's exactly one row per code or farm site in the site information table. So this is what is called a one-to-many correspondence. I'm going to just leave you to read through all of this text that I put about the different types of joins because I don't want to say something wrong. I tried to get it as accurate to my knowledge in here. Again, there are many resources online about the different types of joins. In this particular example, we are going to be using an inner join. But first we have to see what are the columns to join on. So it's going to try and look for any matches between columns that are common among the two tables. So in the site information table, we have CID, code, year, state, county, longitude, latitude, yada, yada, yada. In the decomp biomass table, we have CID, code, subplot, subsample time, etc. CID is not going to match between the two tables because it's an internal identifier for the row in the entire database system. So when we are joining these two tables, we have to explicitly tell it that we want to join on code and only on code. And that's exactly what we're doing here. So we're doing an inner join on the site information table with the decomp biomass table and by code only. So if we run that, you'll see this is a little bit easier to read just because of the formatting. We have cid.x, which is the CID from the first table, which is site information. And then here you see we have 15 more variables, and we have cid.y. That is the same column, but with different numbers from the decomp biomass table. So again, you just have to be really careful, otherwise your joins aren't going to make any sense. You'll have a bunch of things that don't match up. And if we wanted to look at just a few columns so that, what we would actually need to do some analysis, like with biomass and percent in, you can see the query that this runs, which is, a whole bunch of SQL. This is more complicated than you would probably write by hand, but it is, super explicit to account for, any possible errors that might come up from ambiguity. And then this is the table of just a few columns that would be returned. But here you see we have code, year, state from the site information table, and we have code, subplot, subsample time, dry biomass, and percent n from the decomp biomass table. Like I said, you could super simplify that SQL down if you were, really handy about it, to something like this. So if we want to take that query that we just generated and look at only the rows where percent n is not an NA value, where it's already been filled in, then pull it in locally with collect. And you'll see this is what gets returned. You can also see it here. It's what gets returned. And then the second page of our output is this figure where I'm just kind of visualizing from, time 0 to time 5 what the percent n content of the bags were. All the queries that we just did were fairly straightforward. We only did, a join on 2 tables, and we did a little bit of filtering and sorting, but there are much more complicated operations that you can do on the database side. So let's take a look at some of these more complex queries. So we're going to try 3 tables. We're going to take the information from the decomp biomass table so that we can look at the time 0 bags and figure out the ratio of fresh weight to dry weight. Then we're going to look at the in-field biomass table, and we are going to try and figure out the dry weight equivalent of the fresh biomass that was recorded when we collected the bulk biomass. Then ultimately we're going to join it back to the site information table to get all the state and year information. We're going to create some new columns to convert the percent quality from the forage analysis into grams per meter squared. And then we're going to pull the query in locally to do our ultimate visualization and analysis. So this is going to be a lot of steps. So the first step, let's just make a query where we're trying to figure out bag moisture. So we go to the decomp biomass table, we filter for the time 0 bags, we calculate a ratio between dry weight and fresh weight, and then we get a summary for every subplot within every site what the average ratio is. And so you can see what's returned here. They range from 64% to 28%, something like that. So now we need to take this and use it to convert the fresh weights that we got when we collected the bulk biomass into dry weight equivalents, or at least an estimate of dry weight equivalents. So here we're taking the query that we just ran, we're joining it to in-field biomass with a full join, and then mutate. Again, that creates new columns onto a table. And all of these sort of standard math operations, saying which column you want, and multiplying and adding and dividing, figuring out averages, all of those are functions that can be translated directly into SQL. So this is a lazy query, and it happened inside the database. And you can see now we have all these other columns from the forage analysis where we got, crude protein and fat and things like that. And the last column in this is from that query that we generated to figure out what the dry biomass estimate was. So now we are going to take this complex query that is already a join, and we are going to join it again with the site information table. And so here we're doing a full join on site information and our complex query that we've already done. And you can see now we have 35 columns with an unknown number of rows, where we've got code, year, state, yada, yada, yada from site information. We've got all the percent quality values from the in-field biomass. And we have our dry weight estimate that we calculated using the moisture ratio from the decomposition bag table. Another thing we might want to do is convert the units inside the database. So we're going to make some more columns. We're going to use mutate at to generate a whole bunch of columns at once. We're going to look at all of the columns that match starting with percent, and we are going to multiply them by the dry weight estimate and divide by 100 to get the number of grams per meter squared of, for example, lignin or crude protein. And if you want to see what the SQL output of that is, I am scrolling past it here, and I would not want to type any of that out by hand. So now the last thing to do is to pull the data in locally with collect, filter out any erroneous columns with missing data, and you see now we have 259 rows and 51 columns. So you can see we have percent crude protein right here, and then we also have crude protein in grams per meter squared. So an example visualization you might want to do is looking at grams of hemicellulose per meter squared. This is just a box plot. You can see it varies with state and with year. And you could also do some sort of analysis where you're looking at the relationship between two variables. So here we're looking at percent crude protein and our dry weight estimate, and we're splitting it up by year and fitting linear regression to it. So, and of course, don't forget to clean up after and disconnect from the database. That's everything that I've got for you. I hope this was informative and useful and relatively straightforward. If you have any questions, of course, you can contact me. Again, I would really love for you to go through the HTML documents and also play around with these R notebooks yourself so that you can get more familiar with how these queries might work. And I look forward to hearing from you with any feedback. Thanks for watching.